So this is my final lesson, and the one that people I have spoken to were most dreading. This is the lesson on calculations. There are several useful calculations we can apply to acids and bases, which we will cover in this lesson. I will go through each one bit by bit, and then I will give you work-through examples of each one. Please try not to be intimidated. The calculations are relatively simple as long as you follow the method, and I will try to explain the method thoroughly. So, without further ado, let's do this. So the calculations we need to cover are these. We need to cover how to calculate concentration from volume and number of moles, as well as rearranging this equation to give us a way to calculate volume and number of moles. At this stage, it's important to know that 1 decimeter cubed is the same as 1 litre, and 1 centimeter cubed is equal to 1 milliliter. Secondly, we need to cover how to balance equations, as it will always be a useful skill to have, as well as being useful in our titration calculations. Finally, we have the calculations associated with titrations, calculating the concentration of an unknown substance from the titration data. Again, I want to stress that it sounds confusing, but I will go through the methods and do worked examples, and hopefully it will make sense. So the first thing to go over is something that I've mentioned in videos I've presented, calculating concentration, volume, or number of moles. The equation is very versatile as it can be rearranged to give an equation to calculate any of the three, number of moles, volume, or concentration. So firstly, the number of moles equals the volume multiplied by the concentration. This is the first iteration of this equation. The second version of this equation is that concentration is equal to the number of moles divided by volume. The third version of this equation is that volume is equal to the number of moles divided by concentration. Using these three equations, so long as we have 2 out of 3, we can calculate the third one, using one of the equations I've listed. So, for example, if we have the concentration and the volume, then by multiplying concentration by the volume, we can get the number of moles. As demonstrated, this can also be expressed as a triangle, whereby the quantity you don't have, you cover with your finger, and then be left with the equation. So, for example, if you don't have the concentration, cover that with your finger, and you're left with the remaining equation, number of moles divided by volume. Let's go through some examples. So, if a 100 centimeters cubed solution of glucose contains 0.4 moles, what is the concentration? Pause for a minute and try it yourself. How many moles are in 250 centimeters cubed of a 0.4 mole per decimeter cubed solution of ammonia? Again, pause for a minute and try for yourself. Finally, what volume of a 2.4 mole per decimeter cubed solution of butane contains 0.6 moles in total? Pause once more and give it a shot. Answers coming up. Okay then, so first things first. 100 centimeters cubed is equal to 0.1 decimeter cubed. This is the first quantity we need. Secondly, we have 0.4 moles in total. This is the second quantity we need. Using our equations, we know that number of moles divided by volume equals concentration. 0.4 divided by 0.1 is 4. Therefore, the concentration is 4 moles per decimeter cubed. For this second question, the first thing to do is convert from centimeters cubed to decimeters cubed. 250 centimeters cubed is 0.25 decimeters cubed. Since we know the concentration, we then just need to multiply the volume by concentration to get number of moles. So 0.25 multiplied by 0.4 equals 0.1. So we have 0.1 moles in total. Finally, we have the concentration and the number of moles. So all we need to do is divide 2.4 by 0.6 and we get the answer, which is 0.25 decimeters cubed, or in centimeters cubed, 250. Hopefully, you will follow that. If not, go back and review and see if you can get it. As I have said, this is an extremely useful set of equations in chemistry, so it's important to understand them. If this made sense, then let's proceed. So next, we have balancing equations, which is the second part of our puzzle to solve titration problems. Take a look at this equation for the reaction of sulfuric acid with sodium hydroxide. Obviously, from previous videos, we know that these react to form a salt, sodium sulfate and water, so we've put all of this into the equation. However, the equation isn't balanced. To start with, we can note that on the left-hand side, there is 1 sodium atom in total, whereas on the right-hand side, there is 2 sodium atoms. We can only put numbers in front of whole molecules, so to rectify the problem, we have to put a 2 in front of NaOH. This balances the sodium atoms, but unbalances the other atoms. So we can see that the hydrogen atoms are unbalanced now, 4 on the left and 2 on the right. We can also see that the number of sodium atoms are balanced, so we can't alter the Na2SO4. So we have to alter H2O. If we put a 2 in front of the H2O, then we've balanced the hydrogen atoms. At this point, the equation is balanced for the hydrogen atoms and sodium atoms, so now we need to check the oxygen atoms. There are 6 on the left and 6 on the right. Therefore, since all atoms are balanced on both sides, we can consider the equation balanced. To start with, balancing the equation seemed daunting, but once we broke it down, it actually makes complete sense. Although in this example I started going with the sodium atoms, we could have also started with the hydrogen atoms, and it's usually better to do so. Let's go through a worked example. This is our question. We have the reaction of a metal, aluminium, with hydrochloric acid to form the salt, aluminium chloride, and hydrogen gas. This equation is clearly not balanced, as the only thing we currently have that is balanced is the aluminium. Stop for a minute and try this yourself. Answers are coming up. So, let's first look at the chlorines. On the left we only have 1, but on the right we have 3. Now, we could put 3 in front of the HCl, but we also need to consider the H2 on the right. If we put 3 in front of HCl, we would have 3 hydrogen atoms, which does not make a whole number of H2 molecules. We need to find the lowest common multiple of 2 and 3, which is 6. So if we put a 6 in front of the HCl, that would be the first step. The next step is to balance the hydrogen and chlorines. So on the left we have the 6 chlorine atoms, and on the right we have 3. So if we put 2 in front of the AlCl3, then we have the correct number of chlorines. Then we can balance the hydrogens. If we have 6 hydrogen on the right and 2 on the left, we need to put a 3 in front of H2, which also balances the hydrogen atoms. Once we have all of this, we can simply balance the Al atoms, which we have 1 on the left and 2 on the right. So all we need to do is put a 2 in front of the Al. Now if we check all of the atoms, we see they're equivalent both sides, so the equation is balanced. Let's try a second example. This time we have the reaction of sulfuric acid and hydrogen iodide to form hydrogen sulfide, water, and iodine. I know this isn't a reaction of acids and bases, but it's a good example to figure out how balancing works. So, pause for a minute, give it a shot yourself, see how you get on, and then I'll go through the solution for you. Okay, so, first off, we have 4 oxygen on the left-hand side and only 1 on the right-hand side. So to balance the equation on the right-hand side, we have to have 4 oxygen atoms. We only have one place where oxygen exists, so we have to put 4 in front of H2O. This sorts out the oxygen atoms. Having done this, we now have an imbalance of hydrogen. On the right is 10 hydrogens, where the left only has 3. We used the oxygen from the H2SO4 in the previous step, so we can't change that without unbalancing the whole equation. So let's use hydrogen iodide. We have 10 hydrogen on the right and 3 on the left, so by putting in 8 in front of the hydrogen iodide, we then have 10 hydrogen on the left. This balances the hydrogen. All that's left is the iodine atoms. We have 8 on the left and 2 on the right, so putting a 4 in front of I2, we can balance the iodine as well. This balances out the equation, as the sulfur atoms were balanced to begin with and didn't change. Hopefully this made sense. If not, go back and cover this content again. If it did, we move on to tying the two concepts together to allow us to do titration related calculations. Okay, so using the two things we have covered, we can now solve this question. This is a typical titration question, similar to what you might see in your exam. First things first, we need to come up with an equation. We know from previous videos, and have said plenty of times now, an acid plus a base neutralize each other to create a salt and water. Now, when an acid dissociates, H plus is removed from the molecule, so what's left can be presumed to be NO3-. When a base dissociates, OH- is removed from the molecule. In this case, barium hydroxide has 2 OH-, so what's left in the end is Ba2+. Therefore, we need 2 NO3- to 1 Ba2+ for everything to be neutralized. Because of this, we will have 4 hydrogen and 2 oxygen reacting too, which means 2 water molecules. Putting all of this together, we come up with the equation 2HNO3 plus BaOH2 becomes BaNO32 and 2H2O. Now that we have this equation, we need to figure out how many moles of barium hydroxide we used. 25 centimeters cubed equals 0.025 decimeters cubed. If we multiply that by the concentration, we come to an answer that 0.0005 moles of barium hydroxide have been used. Now we go back to the equation. We can see that for every 1 barium hydroxide we use 2 nitric acid. So for the base we neutralized, we need twice the number of moles of nitric acid to moles of barium hydroxide. Therefore, we can say that we had 0.001 moles nitric acid that we used. We can then use concentration equals moles divided by volume to reach the concentration. 12.5 centimeters cubed is 0.0125 decimeters cubed. 0.001 divided by 0.0125 equals our answer, 0.08 moles per decimeter cubed. This is the concentration of the nitric acid that was used in the neutralization. Shall we try the worked example? The last worked example of the video and the classes, you'll be glad to hear. So let's go. We have 30 centimeters cubed of ethanoic acid reacting with 20 centimeters cubed of 1.5 molar sodium hydroxide solution. What mass of ethanoic acid is present in this ethanoic acid solution? Try this question for yourself. Take a few minutes to try and work it out. Remember that we can get the mass from number of moles times molar mass, and that the concentration is number of moles divided by volume. Answers on their way. Okay, so we know that an acid and a base react to form a salt and water, so water will be formed, taking a H plus from the acid and an OH minus from the base. What is left? CH3, COO- and Na+, which come together to make a salt. From this information, we can create a balanced chemical equation for this reaction. We can now use this and our other calculations to find the concentration of the ethanoic acid, and from that the mass in 1 decimeter cubed. So 20 centimeters cubed is equal to 0.02 decimeters cubed. We can then do concentration times volume to find the number of moles, which would be 1.5 multiplied by 0.02, which gives us 0.3 moles used in this reaction. Since the equation has a ratio of 1 ethanoic acid reacting with every 1 sodium hydroxide, we can also assume that we use 0.03 moles of ethanoic acid in this reaction. We also know that we had 30 centimeters cubed, or 0.03 decimeters cubed, so we can do number of moles divided by volume to find the concentration. This is 0.03 divided by 0.03, which equals 1. So the concentration of the ethanoic acid is 1 mole per decimeter cubed. Finally, to find the mass, the amount of ethanoic acid in 1 decimeter cubed is 1 mole. The molar mass of ethanoic acid is 60, so all we need to do is multiply the molar mass by the number of moles to get the weight in grams. That means there is 60 grams of ethanoic acid in 1 decimeter cubed of this acidic solution. That was a little more complicated, so I hope it made sense. So, here we are, at the end of my lessons with you. It's been great fun to come up with these lessons to share with you. I hope you all enjoyed it as much as I have and have been following everything I've tried to teach. Thank you for listening to me as long as you have, and I look forward to you trying the worksheets and the Kahoots. Take care, and good luck with your GCSEs.